the next item I'd like to talk about is inconsistent extruded profile shapes, and this is a windowsill profile that we did some consulting work on. And the problem they had was when they tried to go at a higher production rate, at a more cost-effective production rate, they had unstable production, so they could not maintain the tolerances very well apart. And so they had to stay at relatively low line speeds and production rates. And one of the issues was that they said, okay, well, if we can't go faster, let's build another line. Let's put another line up with the same geometry. And the traditional approach in profile die design is cut and try. And when they ship the die initially, they usually ship it with a tuner, someone that goes along, and then on the plant with a file and maybe some local machining equipment makes modifications to tune in the geometry. And so when they tuned in the die and got it running, it was just running essentially too slow for their production rate, what they needed. And so then the customer says, give me another die just like it, but all those tuning modifications and changes were never recorded. So you have to start that whole process all over again. So they came to us to see if there was a better way. And the first thing that we do is we analyze the existing geometry. So this is the die that was used to produce this windowsill profile. You can see it usually comes in from a circular entry, some maybe 2.5, 3-inch diameter, spreads out. There's a little insert cone there that spreads the material out, and then goes into the mandrel section, which has these vertical ribs in there, and then that mandrel extension goes into the front of the die lip plate, and it's set up to produce this product. Now what we do is we analyze, when you assemble this die, every cross-section on between every plate. And here's the results of the simulation of the cross-sections on this die. So the circle, of course, pretty trivial, so we don't include that. The next cross-section, when these are assembled, looks like this, and you can see that there's a high flow. Red is high velocity, blue is low velocity, and we got very high flow at the edges. Then in the next cross-section, when we analyze the die, the polymer prefers to flow in the center, and see here, there's very low flow over on this edge. And the same is true over on this cross-section. We have perhaps a little higher flow on the edge and some moderate flow in the middle. Then we move to the next cross-section, and this cross-section has very low flow in the center and high flow at the edges. In fact, all these three cross-sections have higher flow in the center and or low flow in the center and high flow at the edges. And the next cross-section, now in order to get the flow into the ribs, they make those channels very large, so you get large high flow in the rib sections, but very low flow all on the outside channels. And then the channels that they eventually tuned at the exit seem to be fairly well balanced in terms of overall flow and how much material you want. But when you look at how the polymer is flowing through this die, it's essentially snaking through the system, wanting to flow from an edge to the center, to the edge, and back to the center. And this is what we refer to as cross flows. And cross flows are a result of insufficient die flow balancing. So to combat this, Compuplast has developed our cross flow minimization method of die design. And I just want to go briefly over that because this method is meant to be used in association with the Virtual Extrusion Laboratory profile die module. So the first part of applying the cross-flow minimization method is to analyze the required part shape. And within the Virtual Extrusion Laboratory, we can import the cross-section and subdivide it into different domains, subdomains. And when we do that, we have the percentage area that each detail in the part represents. So for example, each one of these ribs represent 1.16% of the total area of the part. The lower and upper horizontal walls represent 34% of the total area of the part, and so on. And the idea here in the cross-flow minimization method and die design is that the requirement is that the percentage area represents the percentage mass flow that we want in each one of those areas. So if I was going to produce this part at, for simplicity's sake, 100 pounds an hour, I would have to deliver 1.16 pounds per hour to each one of these ribs if I wanted to make the correct wall. If I delivered less than 1.16%, those walls would end up being too thin. And if I delivered more than that amount, those walls would end up being too thick from the specification. So once we understand what our target is, then we simply go through the different sections. So let's say I'm worried now about this side of the die. How much material do I need to form this part, this section of the profile? Well, each one of those sections represent a certain percentage. When I combine them, I get about 6.9%. Then in the corresponding area of the die, at every cross-section, I need to get this much material delivered to that region. So if I take one of the cross-sections, say early on in the die, we can integrate the flow on this edge and combine those regions, and we can optimize the flow channels to the point where the amount of material flowing there is equal to the amount that's desired. It's very simple. So we make sure that each cross-section of the die has the right amount of flow that's required by the part. So if we were to take this bottom wall, for example, which requires 34% of the total flow, we would make sure that at any cross-section in that die, if we integrated the velocity to determine the percentage flow rate in that area, it would be 34%. Same with the top wall. This top wall wants 34% of the total flow. If we take any cross-section in the die and we have optimized the geometry, once the geometry is optimized, we will have 34% of the total flow flowing in that portion of the die. And so through this section-by-section optimization, we will come up with a die that will be much more optimized, and rather than having the polymer snake through the die using cross flows, we will have a more direct path of the polymer right from the entry all the way to the exit. Now, the big advantage of this, when we're balancing both the inlet and outlet of all plates, is that we improve the process stability. The limitation on production rate is basically the cooling limitation, which it should be for almost all extrusion processes. And our die is much, much less sensitive to any small changes in resin, just things that the resin companies cannot control. And so it's very common for these types of dies that are unbalanced. You get a new lot of material in, you have to go and rebalance the die. You move the die to another extruder, you have to go and rebalance the die. Once the die is balanced through cross-flow minimization, we found that they operate much, much more stable, and they don't care what extruder they're on, and lot to lot variations of the polymer have very little effect on their performance. And this same approach can be applied to multi-lumen medical tubing, use the exact same method, and even to rubber and TPE extrusion for automotive seals. We've also applied the same method for that. Then the last item I want to talk about was co-extrusion, and in this case we're looking at a wave pattern in a 3-layer film sample which appeared, and the customer came to us, and this is the product that they were making, basically a 3-layer product with thick skin layers and a thin core layer of a barrier material. And they were combining the layers in a feedblock, and we do a cross-section of a feedblock and analyze it. It looks like this. So here's layer A, layer B, layer C. And we're seeing on the contour here velocity, and if we look at the details of the numbers here, we have a maximum velocity of about 113 millimeters per second because these lamella were not evenly balanced. The middle layer prior to merging was coming in at about 14.6 millimeters per second at Vmax, and the the three layers were going into a flat die and distributing together, and they were entering the flat die with a maximum velocity of 64.6 millimeters per second. So if you look at this, you can see that the middle layer has to accelerate 4.4 times, going from where it comes in here to where it enters the die. Now, if we look at the space it occupies, you can get an idea of the deformation that that middle layer is experiencing. It comes into this section here, gets a little wider, so it slows down a bit, and then immediately it's stretched down to a very, 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 very thin layer. So this is just like grabbing the material and pulling it and stretching it. Now, this area of high acceleration or high elongation brings out the topic of elongation viscosity. The polymers, in addition to having shear viscosity, have a resistance to stretching, which is referred to as elongational or extensional viscosity. In industry, we refer to it really as melt strength. But the technical term here is elongational or extensional viscosity, and that is when you pull the polymer, it has some resistance in the pulling direction. And some polymers exhibit a strain hardening behavior. Think of this as stretching a rubber band. When you take a rubber band and stretch it, it gets harder to stretch, and ultimately it locks up, and if you put a lot more force on it, you'll break it. Other polymers, for example, HDP, LLDP, which have more narrow molecular weight and smaller side branching, don't have as much entanglement, and they are more strain softening. So when you pull them, they get easier to pull. For example, think of chewing gum. If you take some chewing gum and start to stretch it, the more you stretch it, the easier it is to stretch. And so they have a strain softening behavior. Now, it is possible that if material has a strain hardening behavior and you try to stretch too much, you can tear it. And this is effectively what happens if the co-extrusion system is not designed properly or considers the elongational viscosity of the polymer. So here is a graph from a 2D finite element simulation down the center line of this feed block, and it shows the black line here shows the velocity corresponding to the axis on the left, and the blue line shows the elongation rate corresponding to the axis on the right. And we see that the velocity here is going along at like 16 millimeters per second, and just prior to the merge area where the lamellas taper out, you can see it slows down a little bit, and then it accelerates up to the 64 millimeters per second where it enters the feed block. The blue line represents the elongational deformation that that material experiences. And so it's 0 along here, nothing's happening, and then just near the merge region, the material slows down, so we go actually into compression, negative elongation. The material is slowing down and then rapidly accelerated right in the merge region, and then that decreases down and finally hits steady state and enters the die. Now, this maximum elongation rate is about 3 reciprocal seconds, but the total deformation that the material experiences is really from the min to the max, which is about 4.5 reciprocal seconds. Now, on its own, this number has virtually no meaning. However, when we correlate it to a problem that we're observing, like waves in the product, we say, okay, we know that 4.5 is bad. Now, what's an acceptable number? Well, what we do is on the line when we see a problem, we make some process adjustments. For example, let's take that thin layer in the center and make it thicker so that we're trying to change the amount of deformation that it experiences. And let's find the condition, or let's slow the line down until the problem disappears. Or we make some process change that causes the problem to be corrected, eliminated. And then we determine what deformation was occurring when the problem wasn't happening and compare that to deformation that was occurring when the problem was happening. Once we understand and know a good acceptable value and an unacceptable value, then we can go back to our drawings, modify our designs so that under the correct process conditions that we want, the flow rate that we want, we can minimize the amount of deformation. In this case, we knew that we had to reduce this number by about half. And so the solution was to go back to the geometry, modify the metal of the middle layer so that the gap would be reduced, so that we pre-accelerate this material. So first of all, you can see we balanced out all the other regions, made the lamella more even. So the maximum velocity now here was about 82 millimeters per second. But the middle layer was increased to 26 millimeters per second. Remember, it was 14, so it's approximately doubled. Now, the merging velocity stayed the same because we have the same flow rate, the same gap, and the same geometry within the die. We didn't want to modify the die. So the only change that this resulted in was in the middle layer accelerating not 4.4 times, but 2.5 times. So then when we analyze along a path line down the center what's happening to the material, first of all, the shape shows much less deformation of the material from pre to post merging. And then the graph down the center, the velocity here shows the pre-acceleration right in here. And we can control the rate of pre-acceleration because we can control the angle on the metal for the geometry. And so we get up to our 26 millimeters per second. We still had a little bit of a dip before the merge, and then we had the acceleration to the final velocity of that center layer prior to entering. The maximum elongation rate reduced to about 2 reciprocal seconds, but the total also reduced more significantly to about 2.5 reciprocal seconds. So, making that change was enough to eliminate the appearance of that wave on the final product. And so once we understand that we don't want to deform the material too much, then when we go to build our next die, we can ensure that these criteria are met in that design. A similar problem was observed in tubing and cable jacketing. I've also observed it in pipe co-extrusion. But in this example, I want to show you a multi-layer tubing cable jacketing application. You can see these waves on the surface of the jacket. And when you pull that off, you can see the periodic nature of the variation on this surface. And so it's the exact same phenomenon, but happening on a different type geometry, and this time happening on the surface layer. And when we analyze the merging of this material, so this is the merge region, you can see they have an unusually small gap. And usually people will put a small gap on something when they want to have a very even distribution. They'll use the resistance of this channel to improve the distribution system somewhere back here, rather than optimize the distribution system and then optimize the channel. And what was happening here was slightly different than the wave example that you saw previously, where the material was accelerated too much. In this case, the deformation was negative. The material was decelerated too much. So it was coming through that gap rather fast and then slowing down tremendously. And so the elongation rate difference was minus 125. So this sort of when this problem occurred and the customer called us in a panic, they had no rheology data, no viscosity data. They didn't have time to go get that. They needed to solve this quickly. The only thing that was left for us was based on the flow rates to optimize the deformation. And so the geometry was changed, as you can see here, so that the material merged in a more streamlined fashion, and the overall deformation of the material was reduced by about 10 times. And of course, the end result was the product was much, much more uniform without the waviness that was observed in the original design. So once you understand what to look for, what pictures, what colors look acceptable, what graphs what numbers on the graph are important, then we can avoid the formation of any excess elongation stress. Or if we don't know the viscosity, we can just avoid the deformation based on the velocities of the material during the merging of the individual layers. And then in co-extrusion flow analysis, we can determine what the velocity of the individual layer is either before or after it merges. And then we can adjust the pre-merge velocity because we have little control over the individual layer velocity in a multi-layer system, so that it more closely matches the post-merge velocity, and then we can avoid high acceleration or deceleration of the material to have a more uniform product. So, in conclusion, process simulation provides more information for correlation of material properties, geometry, and process conditions with a particular production problem. Simulation gives better insight into the problems, which can lead to faster and more precise solutions as opposed to the traditional trial and error methods. Finally, I would like to thank you for watching, and if you have any questions, you can reach me via email or my telephone number. And if you'd like to see videos on the software or some of our prior webinars, we invite you to visit our YouTube pages shown here.